Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Hello. I would like to learn more about your work on incorporating physics into machine learning through physics-informed neural networks, PINs. Can you provide an overview of the different use cases of PINs and their implementation methods?
Certainly. Physics-informed neural networks, PINs, have been applied in various use cases where there is a need to incorporate physical laws into machine learning models. Here are some common use cases and implementation methods of PINs. 1. Solving differential equations. PINs can be used to solve differential equations that govern physical systems. By incorporating the governing equations as a part of the training process, PINs can learn the underlying physics and provide accurate prediction. The implementation involves defining the loss function based on the governing equations and training the neural network to minimize this loss. 2.1. System identification. PINs can be used for system identification, where the goal is to estimate the unknown parameters or coefficients of a physical system based on observed data. 1. PINs can effectively learn the relationships between the inputs and outputs of the system, allowing for accurate estimation of system coefficient. 3. Model discovery. PINs can also be used for model discovery, where the objective is to discover the underlying physical laws or equations governing a system. By training the neural network on observational data, PINs can identify the relationships and equations that describe the system behavior. The implementation of PINs involves designing the neural network architecture, defining the loss function based on the physical laws or system identification objectives, and training the network using data. It's important to note that the implementation of PINs may vary depending on the specific use case and the complexity of the physical system. However, the general idea is to leverage both the data and prior physical knowledge to train the neural network effectively.
Thank you for the thorough overview of the different use cases and implementation methods of PINs. It's fascinating how PINs can solve differential equations, perform system identification, and even discover underlying physical law. Could you provide some examples of real-world applications or case studies where PINs have been successfully used in various engineering domains?
Certainly. PINs have been successfully applied in a wide range of engineering domains. Here are a few examples. 1. Aerospace engineering. PINs have been used to optimize the shape of aircraft wings to improve aerodynamic performance. By training the network on computational fluid dynamics simulations, engineers can quickly explore a large design space to find the optimal wing shape for reduced drag and increased fuel efficiency. 2. Civil engineering. PINs have been employed to predict the behavior of structures such as bridges and buildings under different loading conditions. By training on data from sensors embedded in the structures, engineers can monitor structural health, detect potential failures, and optimize maintenance schedules. 3.1. Biomedical engineering. PINs have been used in medical imaging application. For example, in magnetic resonance imaging, MRI, PINs can be trained to reconstruct high-quality images from undersampled or noisy raw data, reducing scan time and improving image quality. 4. Energy systems. PINs have been utilized in optimizing energy systems, such as wind farms and power grids. By training on historical data and incorporating physical laws, PINs can predict energy demand, optimize energy generation and distribution, and improve the efficiency of renewable energy systems. These are just a few examples, but the potential applications of PINs are vast and varied. They can be applied in fields such as robotics, materials science, chemical engineering, and many more. The versatility of PINs allows them to tackle complex problems in different engineering domains, making them a powerful tool for interdisciplinary innovation.
Thank you for providing such diverse examples of real-world applications of PINs. It's impressive to see how PINs can be applied in aerospace engineering, civil engineering, biomedical engineering, and energy systems, among others. In these applications, how do PINs enhance model training compared to traditional machine learning approaches, that do not incorporate physics.
Pins enhance model training compared to traditional machine learning approaches by incorporating physics-based constraints into the training process. Traditional machine learning approaches rely solely on input-output pairs to learn patterns and make predictions. However, pins go beyond this by incorporating the governing differential equations of a physical system into the training process. By incorporating physics, pins ensure that the predicted outcomes not only fit the available data, but also satisfy the underlying physical laws. This means that the models trained using pins are not only data consistent, but also physically plausible. This is especially important in applications where adherence to physical laws is crucial, such as in engineering, physics, and other scientific domains. Furthermore, pins are well suited for modeling complex and nonlinear systems. Traditional machine learning approaches may struggle with such systems, but pins with their universal approximation capability can effectively model and simulate these systems. In summary, pins enhance model training by incorporating physics-based constraints, ensuring physical plausibility, and effectively modeling complex and nonlinear systems.
Thank you for explaining how pins enhance model training by incorporating physics-based constraints and ensuring physical plausibility, especially in complex and nonlinear systems. This integration of physics into the machine learning process is indeed valuable in various domains. In terms of implementation, what are some common challenges or limitations that researchers encounter when using pins? Are there any strategies to overcome these challenges?
One common challenge that researchers encounter when using physics-informed neural networks pins is the lack of labeled training data for the physics-based problem they are trying to solve. Unlike traditional machine learning tasks, where large labeled datasets are often available, physics-based problems may have limited or sparse data. To overcome this challenge, researchers can use physics-based constraints or equations to guide the training process. Pins are designed to incorporate physics principles into the learning process, which means that even with limited data, the network can still learn the underlying physics and make accurate predictions. By formulating the problem as a partial differential equation, PDE, or a set of governing equations, researchers can incorporate these equations as loss terms in the network's objective function. This ensures that the network adheres to the physics while learning from the available data. Another challenge is the computational cost associated with training pins. Solving complex physics-based problems often requires a large number of iterations and a significant amount of computing power. This can be a bottleneck, especially when dealing with high-dimensional problems or when training on large datasets. To address this, researchers can leverage parallel computing techniques or utilize high-performance computing resources. Techniques like mini-batch training, where the training data is divided into smaller subsets, can also help reduce the computational cost. Additionally, researchers can explore model reduction techniques, such as reduced order modeling or dimensionality reduction, to decrease the complexity of the problem and make it more computationally tractable. It is worth mentioning that parameter tuning is another challenge researchers face when working with pins. The performance of a pin model heavily depends on various hyperparameters, such as the learning rate, batch size, and network architecture. Finding optimal values for these hyperparameters can be time-consuming and require extensive experimentation. To address this challenge, researchers can use techniques like grid search or random search to systematically explore different combinations of hyperparameters. They can also leverage tools like automated hyperparameter optimization algorithms or model selection techniques to efficiently find the best hyperparameter value. Additionally, transferring knowledge from previously trained models or using pre-trained models as initializations can help speed up the parameter tuning process. Overall, while there are challenges and limitations associated with using pins, researchers can overcome them by leveraging physics-based constraints, utilizing computational resources effectively, and employing systematic approaches for hyperparameter tuning. By doing so, they can harness the power of pins for a wide range of applications in different engineering domains.
Thank you for outlining the common challenges and strategies to overcome them when using pins. The scarcity of labeled training data in physics-based problems can be addressed by incorporating physics-based constraints and equations as loss terms in the network's objective function. Additionally, leveraging parallel computing techniques, model reduction methods, and systematic approaches for hyperparameter tuning can help overcome the computational cost and parameter tuning challenges. These strategies can enable researchers to effectively utilize pins in various engineering domains.
When it comes to implementing physics-informed neural networks, PINs, researchers often face a few common challenges. These challenges include 1. Limited data. WIM. One challenge is that physics-based problems often have limited data available for training the neural network. Coding neural network. Unlike traditional machine learning problems where large datasets are common, physics problems may have limited or sparse data points. Incorporating physics constraints. Another challenge is incorporating the known physics constraints into the neural network model. It is crucial to ensure that the neural network respects the physical laws and constraints in order to obtain accurate predictions. 3. Computational efficiency. Pins can be computationally expensive, especially for complex physics problems. Training the neural network and solving the physics equations simultaneously can require significant computational resources and time. To overcome these challenges, researchers can employ various strategies. 1. Data augmentation. Researchers can use techniques to augment the limited dataset by generating additional synthetic data points. This can be achieved by perturbing existing data or generating data through numerical simulation. 2. Incorporating physics equations. Researchers can include the known physics equations as a part of the neural network architecture. This can be done by adding specific layers or loss functions that enforce the physics constraints. By doing so, the neural network can learn to respect the underlying physics principles. 3. Adaptive learning. Researchers can use adaptive learning strategies, such as adjusting the learning rate or employing early stopping technique, to improve the computational efficiency of training the pin. These techniques help in optimizing the training process and reducing the computational resources required. 4. Parallel computing. To tackle the computational demands of pins, researchers can leverage parallel computing techniques. This involves distributing the computational workload across multiple processing units, such as GPS or cloud computing resources, to speed up the training and inference processes. Overall, by employing these strategies, researchers can overcome the challenges associated with implementing pins and develop accurate and efficient models for physics-based problems.
Thank you for summarizing the common challenges researchers face when implementing pins and providing strategies to overcome them. Data augmentation techniques, incorporating physics equations into the neural network architecture, adaptive learning strategies, and parallel computing can all contribute to addressing the challenges of limited data, incorporating physics constraints, and improving computational efficiency. These strategies enable researchers to effectively utilize pins and develop accurate models for physics-based problems.
When implementing physics-informed neural networks, PINs, researchers may encounter several challenges. One common challenge is ensuring that the network satisfies the governing differential equations, GDS, accurately. Another challenge is choosing the appropriate number and distribution of collocation points for calculating the residual. To overcome these challenges, researchers can employ various strategies. One strategy is to carefully design the architecture of the neural network to ensure that it has sufficient capacity to approximate the solution to the GDS accurate. This may involve increasing the number of hidden layers or adjusting the number of neurons in each layer. Another strategy is to use a refinement process for selecting the collocation point. Initially, researchers can start with a small number of collocation points and gradually increase their number based on the performance of the network. This iterative refinement approach helps in improving the accuracy of the network's approximation. Furthermore, researchers can use adaptive sampling techniques to choose the collocation points intelligently. These techniques use information from the network's predictions and the residuals to guide the selection of collocation points in regions where the network's accuracy is low or where the GDs are more sensitive. Additionally, regularization techniques can be employed to ensure that the network does not overfit the training data. Regularization helps in preventing the network from memorizing the data and instead focuses on learning the underlying physics. Lastly, researchers can leverage transfer learning techniques by pre-training the network on related problems or using pre-trained networks as initializations. This helps the network to learn general patterns from existing data before fine-tuning it for a specific problem. By employing these strategies, researchers can overcome challenges and improve the accuracy and effectiveness of physics-informed neural networks, PINs, in solving real-world problems.
Thank you for summarizing the challenges researchers may encounter when implementing PINs and providing strategies to overcome them. Designing the neural network architecture appropriately. Refining the selection of collocation points. Using adaptive sampling techniques, employing regularization, and leveraging transfer learning can all contribute to addressing challenges related to satisfying the governing differential equations, GDs, accurately, and choosing the right collocation points. These strategies help improve the accuracy and effectiveness of PINs in solving real-world problems.